What if the secret to a habitable planet and the cause of our current climate crisis were the exact same thing? Well, they are. And that thing is carbon. Think of it as the engine of life and Earth's master thermostat. But right now, we are cranking the dial on that thermostat without really grasping the consequences. In this explainer, we're going to break down that planetary engine, see how it's supposed to work, and understand why we're pushing it towards a dangerous breaking point. So here's how we're going to break it down. We'll start with the building block of life itself. Then we'll get into the two engines that power our planet's climate. We're going to travel back in time, deep time, to see what happens when those engines get out of whack, and then we'll look at how we're pushing them to their absolute limits today. And finally, we'll look at the road ahead, how we might get back to some kind of balance. Ready to take a look under the hood of the engine that powers our world? Let's get into it.
Okay, let's start with the most fundamental question there is. What makes life itself possible? The answer, it turns out, is all around us. It's in the very air we breathe. It is, of course, carbon.
So why carbon? I mean, why this one element? Why not its next-door neighbor on the periodic table, silicon? The answer is all about its unique talent for chemistry. It's just brilliant at forming the long, complex, and stable molecules that are the literal architecture of life.
Okay, check this out, because this slide really gets to the heart of it. It's basically the difference between life and rock. When carbon hooks up with oxygen, you get a gas, CO2, that can float around, cycle through the atmosphere. It's mobile. When silicon does the same thing, you get a solid, silicon dioxide, sand. You literally can't build a world that breathes out of sand. It's carbon's special knack for linking up into those long, sturdy chains that gives us everything from the DNA double helix to complex proteins. Without it, life as we know it just wouldn't be a thing.
So we've established that carbon is the MVP of life. But how does the planet manage this incredibly precious element? Well, the best way to think about it is like a giant machine running on two engines. One is super fast, the other's incredibly slow, and for millions of years, they've worked in almost perfect harmony.
The fast engine is basically the pulse of the planet. It's the constant breath of the biosphere. This is the carbon cycle of life itself. This rapid, non-stop exchange of carbon between the air, the oceans, and every single living thing. It operates on a time scale we can understand, from the rhythm of a day to the span of a human life.
In the scale of this, it's just staggering. Every single year, plants and tiny phytoplankton in the ocean pull about 120 billion tons of carbon out of the atmosphere. That carbon then travels up the food web and gets returned to the air through breathing and decomposition. For eons, this has been a beautifully balanced, self-correcting loop. It's what keeps our planet hum.
All right, now for the second engine, the slow geological one. If the fast cycle is the planet's heartbeat, this is its deep, slow breathing. This is the planet's master thermostat, the process that has regulated our climate over millions and millions of years, keeping Earth in that just right habitable zone. So how does this planetary thermostat actually work? Well, it's pretty ingenious. Let's say the planet gets too warm, maybe from a bunch of volcanic eruptions pumping out CO2. The thermostat kicks in. That extra CO2 in the air makes rainwater a tiny bit more acidic, which in turn dissolves rocks faster. This process pulls carbon out of the atmosphere. It washes into the oceans and gets locked away in sediments and rocks. The planet cools back down. It is an amazing self-regulating system that has kept Earth livable for billions of years.
So these two engines, the fast and the slow, have kept our world in this really delicate balance. But what happens when that balance gets thrown off? What happens when the engines fall out of sync? Well, Earth's own geological history gives us some pretty stark warnings.
Let's hop in a time machine. We go back to the Carboniferous period, this incredibly lush, swampy world. There was so much plant life that grew and got buried that it formed these massive coal deposits we use today. All that burial sucked CO2 out of the sky and plunged the planet into a deep ice age. Okay, now flash forward to 56 million years ago. A huge natural burp of carbon into the atmosphere triggered a rapid and catastrophic warming event that scientists call the PETM. These ancient events are a crystal clear warning of just how sensitive our climate is to the carbon cycle.
Now, here's the absolute crucial point. That PTM warming event was catastrophic for life at the time, but it was a catastrophe in geological slow motion, unfolding over thousands of years. This gave the planet's systems at least some time to try and adapt. Today, we are releasing carbon at a rate that is at least 10 times faster. We are not in slow motion anymore. We're in a high-speed collision with planetary physics, and the natural systems simply cannot keep up.
Which brings us to right now. We have effectively hot-wired the entire planet's climate system. We are taking hundreds of millions of years worth of buried carbon, that ancient fossilized sunlight stored in coal, oil, and gas, and we're injecting it into the fast cycle in what amounts to a geological blink of an eye. We've short-circuited the whole system, and the consequences are now just impossible to ignore.
For almost a million years, atmospheric CO2 has danced up and down in this really stable range. But just look at this graph. In a little over 150 years, we have completely shattered that stability. We've driven CO2 levels more than 50% higher, to a point the Earth hasn't seen in at least 800,000 years. And you can see it right there on the chart. That line is getting steeper. It's accelerating.
So, where are we at this very moment? The latest global carbon budget tells a bit of a mixed story. The good news is that emissions from things like deforestation, they're actually going down. But, and this is a huge but, emissions from burning fossil fuels are still rising. They hit another record high. The net result? We're kind of stuck in this dangerous holding pattern where total emissions are flat at a level that is just completely unsustainable.
And to put this in the bluntest terms possible, the science is crystal clear. We have an incredibly small window to act. This number? This represents what's called our remaining carbon budget. How much we can still emit and have just a coin flip chance of keeping warming below 1.5 degrees Celsius. At the rate we're going, that budget is gone in 4 years. The clock isn't just ticking, it's screaming at us.
So what really happens when you overload the fast carbon cycle this much, this fast? It's not just about turning up the heat. We are fundamentally rewriting the chemistry of our planet's most basic life support systems, and the consequences are going to be with us for generations. You know, through all this, the ocean has been our silent savior. It's acted like this gigantic planetary sponge, soaking up a truly staggering 90% of the extra heat we've trapped and over a quarter of the CO2 we've pumped out. But this incredible service has come at a terrible price. The ocean is getting warmer, it's becoming more acidic, and it's getting fundamentally less hospitable to life.
As the ocean takes on more CO2, it forms carbonic acid, which makes the water more acidic. Someone brilliantly described this as creating an osteoporosis of the sea. It literally makes it harder for crucial creatures at the bottom of the food web, things like corals, shellfish, and plankton, to build their shells and skeletons. The very foundation of the marine world is being eaten away.
And these impacts are creating a domino effect across the globe, kicking off these really dangerous feedback loops. The Arctic tundra, for example, used to be a vast carbon storage unit. It has now flipped and is starting to become a source of emissions. The thawing permafrost underneath it holds a ticking carbon time bomb, twice the carbon that's currently in our entire atmosphere. And when we destroy coastal habitats like mangroves, we release a flood of stored carbon at a rate that's comparable to the annual emissions of a major industrial nation like the UK.
Okay, so we've seen how the system works and we've seen the scale of the mess we're in. The unavoidable question now is, what on earth do we do about it? How do we even begin to close this broken loop and steer toward a safer future? The science is now totally clear on this. It's not enough to just stop digging the hole we're in. We also have to start filling it back in. And that means we have to do two big things at the same time. On one side, we have to protect and restore the planet's own powerful solutions, our forests, our soils, our wetlands. And at the same time, we have to get really serious about inventing and scaling up technologies like direct air capture that can physically pull all that old legacy CO2 out of the atmosphere and lock it away for good.
For billions of years, the carbon cycle has been the engine that created this amazing, habitable world, the perfect conditions that allowed us to evolve and thrive. The ultimate challenge of our lifetime, maybe of all time, is to finally learn how to live in harmony with that engine, to respect its non-negotiable limits, and to build a civilization that can actually last. The future of our planet and our species really depends on it.